Morning, Professor Nyberg. Basically, I'm here to present my capstone on secure NLP inference. It is a capstone that I performed under the mentorship of Professor Wenting Zheng. And let's get started with the introduction to the problem. So basically, with the advent of cloud computing, a lot of the machine learning workloads are migrating to the cloud as, say, machine learning as a service. And the problem in this paradigm is that if you have trained your model on sensitive data and are exposing this model on the cloud, or once this model has been exposed and the clients are performing inference on sensitive data, you risk leakage of data if any party involved is curious or compromised. And what we are trying to build in this capstone is a solution for this, basically making NLP models oblivious that would allow secure inference on a trained BERT model without revealing any information about the client's input data. And such a service can find its use in, say, audits or recognition of a disease mentioned in, say, medical reports, etc. And when I started with this capstone, what was interesting was that there wasn't many works on NLP. So it's as late as 2016 when security started working on logistic regression or simpler models like smaller neural nets.
You sharing your screen? I think you are.
Yeah.
Oh, you want your camera on.
Okay. Sure. So yeah, I was talking about how in 2016, the security community started working on, say, smaller neural nets. And now we have come to, say, ResNets or something more complex, but there are not many works in NLP. So this is a great direction to work on and push research forward. The problems with this particular model is that they're too large. So when you kind of encrypt data or encrypt and then perform operations on it, you kind of introduce a lot of computational overhead, which kind of slows things down and makes it impractical. Secondly, for nonlinear functions, usually you have to kind of approximate the values to kind of operate on them in a secure fashion. And if the model is very deep, which it is in case of BERT, the error can propagate through the layers and amplify. Thirdly, when you're dealing with security, you might have to impose mathematical structures on the input, which might expect your input to be, say, all integers. So when you're emulating fixed point behavior, you might have to scale up and down, and this truncation can also hurt your accuracy. So these are the three biggest challenges that we'll be dealing with while coming up with a solution for the problem. The hypothesis that we are basing our project on is that inference on BERT models can be made oblivious. That is, it can be conducted without revealing information on the training or input data for inference, while maintaining efficiency and accuracy. And the intended users for this work, firstly, would be the academic community. As I said, we are pushing the research forward in secure ML, secure AI. So this would be the next logical step towards this. And also, this work would be useful for machine learning as a service platforms, although academia is pretty ahead of practical applications. So this would be down, say, a few years later when our solution has been optimized further through more research. Coming to our fall goals for this semester, how we approach our solution is by first coming up with a plain text baseline. This is the step where we decide what model we are using, what activation functions would be involved. Can we introduce something like a sparsity or adapters, etc., to enhance on the operations so that our security or the secure operations can be made more efficient. And the next step, once we have decided on the plain text baseline, is how to emulate this plain text baseline using in a black box fashion using our security primitives. And there we question about how to optimize on, say, the linear layers, because there'd be several different primitives for that, versus how to optimize for the non-linear layers, where again, accuracy and performance trade-offs come into the picture. And finally, once we have emulated the plain text model and optimized on bottlenecks, we finally wanted to publish our results by testing our solution on its generalizability. So would it expand to different data sets, different models, perform exhaustive error analysis on what we have done, and finally write a paper to kind of present our ideas to the academic community. So first step was just deciding the baseline. And here, as I mentioned, our efforts are to get a plain text model with certain characteristics that can benefit our oblivious evaluation. So an example of that can be sparsity. In security, there are papers like Gazelle, which is a paper that was presented in Usenix around 3 years later, 3 years earlier, which kind of presents how fast matrix multiplication can be done on sparse encrypted matrices. And there's also some work on sparse NLP models in the NLP field, which kind of reduces the complexity of the model. And so when we plug the sparsity into the picture, we can maybe benefit both in terms of security and in terms of the NLP. And so we performed several experiments on different data sets to kind of get these accuracy results so that we can kind of emulate them once we are performing our black box evaluation. Another property can be introducing adapters so that we can fine tune our models towards the very last layers. And with these few operations, we can further improve on the accuracy performance of our model. And again, we performed several experiments to get baseline results on adding different sparsities to the model itself and to the adapters as well. And we did that using an Intel model, which is basically this paper that Intel worked on a few years earlier, and they kind of expose an open source implementation of this so that we can just plug in our sparsity parameters and get a glue score. Secondly, once we had our baseline results ready, what we had to do was think about how to black box the evaluation. And there are two traditional approaches in security that can help us do this. Firstly is homomorphic encryption, which basically allows you to compute different functions like multiplication or addition on encrypted values. So the value remains hidden and you can perform these operations without actually revealing the value, and you don't need to know the encryption key or decrypt it. So that is the first traditional method. The second is secure multi-party computation, where our intention is the same. Again, multiple parties are coming together to compute on a function and they don't want to reveal their inputs. But here, how we do that is by splitting the input into randomness and distributing this randomness among our participants, and they can locally compute on these values. And finally, after that computation, once you combine all these results, you should get the output that you would have gotten if the input was operated on in plain text. Both of these approaches have their own trade-offs. So HE basically works well when you have small multiplicative depth, basically when you're working with linear functions. If you're not doing that, you kind of have to work with HE-friendly activation functions in the nonlinear layers. So you have to use, say, a square function instead of sigmoid or ReLU, which kind of hurts your accuracy. And even then, this method would be too slow for the nonlinear layers. And for secure MPC, even though you can get accuracy that matches plain text by increasing the precision bits, but here the communication cost is too high. So we usually don't do large operations, say like a huge matrix multiplication. Rather, we depend, say, on evaluating the nonlinear layers through this approach because it guarantees accuracy to a greater extent. So the idea that we base our work on is that we'll use HE for our linear layers and MPC for our nonlinear layers. And now we study the BERT model itself and what is linear and what is nonlinear in this model. So basically the BERT model has around 12 layers of encoders, and each layer of encoder would have a matrix multiplication, some softmax computation, layer normalization, and a GLU function. To assimilate the operation that we'd have to do, in the linear part, we'd have to do the matrix multiplication. And on the nonlinear part, we'd have to do softmax computation, GLU, and a layer normalization, which is basically a division. So early on in the project, once we had decided on this hybrid approach, I kind of went through the model and decided on what parts of the model need to be worked on with MPC or secret shares. So that is the yellow boxes that you see, and the red boxes are the ciphertext, which is the HE approach that we use. So this was a clear way of communicating with my mentor on what I'm assuming would work with HE and what would work with MPC. And yeah, this is what I'd be emulating on. That is what I've experimented on in plain text and what I'd be trying to perform in a black box fashion as well. Now coming to the linear layer part, basically I'll go over an abstraction of what HE does. So HE takes, given a vector of inputs, if you need to encrypt it, you'd basically be adding noise to each of these input values. And that is what we're seeing here. The plain text would be 22 bits. We add some noise and it becomes 64 bits. This is kind of a mapping for the input to, say, a lattice-based structure that would then allow us to perform computation like addition or multiplication in a hidden fashion. And then you can map it back using a decrypted function to get to plain text. And I didn't want to go into the details of how, like the mathematical details of how to optimize on matrix multiplication, because that would be too complicated for the presentation. But so far what we have achieved is that by you coming up with a technique to kind of pack these ciphertext properly and keeping in mind the underlying lattice structure, we have reduce the amount of matrix or multiplication operations that we need to do. And this has resulted in a 24% runtime improvement as compared to Gazelle, which is the state of the art for matrix multiplication that was presented in Usenex, as I mentioned a few slides earlier. So that is the first result that we have got on the optimizations of the linear layer. So we are very optimistic about our results and are targeting for a good conference because these results seem very promising. So this was a linear layer part. The non-linear layer part has its own challenges. Basically, MPC has several techniques that you can pick up, which allow for a trade-off between accuracy and performance. So the first technique can be simply polynomial approximation on the secret shares that I mentioned in the introduction. This is very fast, but might not be accurate enough because, say, the polynomial approximation can be a Taylor approximation with a degree 5 polynomial. And then if you are scaling up and down and truncating, you might lose on the accuracy in this procedure. The second approach is garble circuits, which basically means you kind of come up with a Boolean circuit that hides or garbles these values, intermediate inputs that you're processing. And while this approach is very accurate, it also involves a very high communication cost where basically one party has to send the entire circuit to another party and the keys involved in the garbling as well. The third approach is a lookup table approach, where basically you would try to perform oblivious lookups to a lookup table that already contains the value or the evaluation of the function that you're trying to evaluate. And here the accuracy and the performance depends on the size of the table, but it's very intuitive that if the table is too large, we're basically trying to fit in more values. So the accuracy would be more, but the runtime would be hurt. So we are currently studying these trade-offs and how to decide on what technique to go for. The first thing that we're doing is just an error analysis on different approximation approaches. That would help us decide whether polynomial approximation is appropriate for certain ranges or certain functions. So say for GLU, what we did was basically take up these two very popular methods of, say, Ramez method, which is used in libraries like NumPy to approximate GLU, because GLU is basically X times the error function of X. So it's an integral and it has to be approximated even in plain text. So that kind of gives us the idea of that maybe polynomial approximation is the way to go, because even in plain text, that's what is being done. And so that is the first method. And the second method is something that is used in Boost library, which is a very popular library for C++. And what we found was, and we did these experiments for different quantizations, for different fraction bits, because again, we'd be playing around with the precision bits and the input layer integer to floating point conversions. And what we found was that around 0, the error was pretty less, but when we went to, say, the range of minus 2.5 to 2.5, around that value, the error was kind of high. And then beyond that, for very high values, because GLU kind of just returns X on these higher values, the error is 0. So this study kind of allows us to maybe use polynomial approximation for values that are closer to 0. And our analysis on the input distribution for our model kind of tells us that, yes, most of the majority of the values in GLU for all the layers is distributed around 0. So yeah, we can just experiment more and kind of get a range that that this method is applicable for while thinking of the trade-off between error and performance, because again, as I mentioned, polynomial approximation is the fastest method among the three that we are tackling. Secondly, we are also studying the input distribution of basically all the functions for all the layers. So again, we can come up with what LUT, the lookup table that we need to come up with, or even for garbled circuits, if certain inputs are more concentrated towards a region, maybe to get more accurate results, we can go for garbled circuits even just for that range. So these are our input distributions for, say, the softmax function for two data sets, SST2 and MNLI, and for all the layers. So we kind of saw this pattern where most of our inputs were very small, say -20, and then 20% of our inputs were concentrated around 0. But this is something where generalizability comes in. So we'll have to experiment more to kind of base our solution on this observation. But yeah, these are the kind of tests that we are doing to kind of get an idea of what approach to go for the nonlinear layer. Finally, coming to where we are with the project and what we intend to do. As we started the semester, our plan was to start with a literature review in the first month and come up with, say, theoretical bounds on the approximations that we'd be using, empirical solutions, so coming up with a baseline model. These steps have been on track. In the third month, we kind of tried to improve the accuracy of the baseline, come up with cryptographic solutions for different layers. And we're done with the linear layer part, but that took us a longer time than we expected. So even though we expected to kind of be done with even the nonlinear layer, that would kind of be pushed to the next 2 weeks. And so the subsequent steps of writing a paper and that would also be pushed to, say, January. So that is the plan for now, where I would basically be implementing and studying the trade-off that are involved with the different layers of the different approach for evaluating the nonlinear layer. I would be implementing the end-to-end solutions once I have the optimization for both the linear and the nonlinear layers. I would finally experiment for generalization results, because we don't want to the solution to just be specific to a data set or just to certain model parameters. And finally, yeah, we'll target a public a conference by, say, January, if we can like get our results by then, or February. But yeah, I'll continue to work on this in the upcoming months. And yeah, that is it. I'm open to any questions.
So a couple of comments about the presentation. Boy, I better. Okay, so a couple of comments about the presentation. I think the motivation is clear, and the potential impact of the work is obviously pretty great. I think if you're going to do this presentation to sort of non-experts in the future, you definitely want to add a few slides in the beginning to explain typically how encryption works, you know, what's a glue score, that kind of stuff. Because I think when you get to the slide about what the issues are with encryption in general, it would be nice if someone kind of understood, you know, what the workflow or process is. The other question I had was, it's obviously very insightful to study the input distributions of the different layers in the model, because obviously you want to pick the right encryption based on what you're actually going to be encrypting. But how do you decide that the distribution that you're observing is you know, close enough to the distribution that you're going to see in actual practice? I mean, are you sampling the right global inputs so that you can sort of make that assumption? Or is it that every layer, because of its mathematical nature, is basically going to be limited to a certain distribution, and no matter what the inputs are, you can discern that distribution after, like, say, n samples?
So yes, basically that again comes to our concern with generalizability and like whether observations are correct and expand to a global set. And for that, I'm studying the theoretical structure of the layers, and that is also a next step involved, just making sure that these observations are concrete and can be used to base our solution on.
So how are you generating the distributions now? What data are you using? Just the test data set for the models?
Yeah.
So I think that's, so at some point, you have responsibility for, the quality of your algorithm, but you don't really have responsibility for saying that, okay, for this BERT model, this is the best, test set or evaluation set. And we all know that in reality, hackers try really weird inputs trying to break models, right? And so there's like especially when you're talking about natural language, there's an infinite possible set of inputs because natural language is, generative, right? So I think at some point that's going to be an interesting part of this security guarantee, right? I'm only going to have a finite number of inputs to observe the model, but then I want to put the model out into the wild, right? So it may be that it's possible to construct a proof, which would be super cool. But if it's not, then I think the argument is going to rest on sort of, how comprehensive, the sampling was, or whether you can make some, statements or theorems about the math. Okay. So I think the only other question that I have for you right now is, you're still working on nonlinear layers. You had 3 possible approaches there, and you didn't show me anything that was like a plan for the remaining work, broken down on a week-to-week schedule. I don't know what the risks are. Are all 3 of those going to be things that you can actually explore and evaluate in a few weeks, or are you going to have to make some choices about what to look at there? Are you really familiar with all 3 of those, or could it be that once you start reading about one of them, take you a lot of extra time to figure out? So tell me why I should be confident that you're going to get something done in January.
Three things to address that. I think firstly, basically these are other single pieces. I skipped over some slides, but in my slides are pretty comprehensive and they do involve the risks and challenges and the other system functionalities and more details about that, because I just wanted to focus on some
Yep.
And secondly, third, I am familiar with all 3 approaches. I have worked on them for different neural network solutions. That is one. How do I go about it? I'm not certain about the steps that I would need to take, because it's kind of governed by what results I get with each step that I'm taking. So currently, as you said, that I'll be studying this theoretical structure of the models to kind of see whether the observations can be used to base my solution on. If that's not the case, then again, it's fine, because we're making these broad trade-offs just to get to as accurate as possible. But if that's not possible, then maybe we can just go with one solution. And all these 3 techniques have been used in different ways, so they can be depended on. They have their security guarantees that would expand no matter what. This is just to get that extra edge in terms of performance or accuracy. And why I can wrap up by January is because, as I said, the optimizations that we've gotten for the linear layer are strong enough. We just want to come up with the end-to-end solution and maybe give some contributions to the non-linear layer.
So you have a decision to make, which is you're actually graduating in May, right? Oh, you're graduating in December. Okay. So I think then what you need to do is, by the time that the final report is due, you want to hand something in that's pretty holistic. I think if you were graduating in May, then you could have an option of, taking an incomplete this semester and then finishing all of the remaining work. And then getting a full grade in the spring. But if you're intending to graduate in December, then basically what you should do is write your report with the idea that, the linear result is like the showcase, let's say, of what you've got done. And then whatever additional results you have, or progress reporting, if you will, on non-linear layers, that would be great. And then I think the focus of the report should be, rather than having a complete end-to-end model. Here's all of the observations and learnings and important findings kind of thing. With the idea that if it was going to be like a workshop paper or something like that, we should put in kind of share. Okay. Let's see. Yeah, because I think the obvious thing here is that you have several nonlinear layers, and then you have your three approaches, right? So I'm imagining an M by N matrix where it's going to take a certain number of hours or days, to get through each of those, right? And I think if you're committed to finishing this up and continuing the collaboration with Ting, it's really not an issue. Keep doing that and finish after you graduate. I just want to make sure that what you hand in for your final report is very coherent and well encapsulated, so that TAs don't complain that this is incomplete work or something like that. So you need to make sure that the narrative includes a discussion about how you changed your scope from the beginning and all of that stuff. It's perfectly fine for an exploratory one-person project to sort of end up in a particular place that might not be everything that you want to do, but you need to explain why that is, so that people don't think that it's just because you didn't work too hard, or you're not that smart, right? So, and I think from all of the materials and presentations that I've reviewed, I think I'm pretty confident that those are not the case here.
Yeah.
All right, very good. Do you have any questions for me about how to finish up or how to finish the report?
I think, yeah, you put in the report the balance between, say, communicating these ideas and setting up to what encryption is or what is trade versus going over this.
You don't have to go over what encryption is in your report. You can basically cite all the right references, and then assume that the reader will go off and read those intros or whatever before they read those. You don't have that luxury when you do a live presentation, so it's usually a good idea to have a couple of slides for newbies, but not the report. Just cite the area and what you think the right background references are. And if there are any foundational papers, particularly in your area,
Yeah, thank you.
all right, thanks.